In the beginning, there was nothing. Then man decided to rub two rocks together, and lo and behold, fire was made. Through a series of similar innovations, the internal combustion engine was produced. But this brought its own set of issues into the lives of people, and we quickly tired of lifting these heavy engines by hand. The engine hoist was subsequently developed. This project looks at the material selection process for this great innovation. Specifically, we chose the 2-ton engine hoist made by Northern Tools because it had easily accessible specifications. This hoist lifts up engines of up to 2 tons by grappling onto them with a hook and pumping fluid into a hydraulic cylinder, which exerts a force onto the structure, pulling the engine off the ground. For the material selection process, we looked at finding a material for the structural frame of the hoist. After asking the manufacturer of the parts in China, we were told that the material is made of cast iron that is hot rolled into the proper shape. Although it is not a common way of forming cast iron, hot rolling has the advantage of being able to make thin sheets, which are common in the design of the hoist. The parts are then welded together and shipped off to America, where they are assembled and further shipped off to vendors such as Home Depot. The hoist is designed to lift up engines, hold them for long periods of time, and then gently place them in the desired location after use. The hoist has a 1-year warranty, so regular maintenance, including lubricating the parts and inspecting for any cracks, is required in order to ensure the hoist is in working condition for a long period of time. In order to come to our own conclusions on what material to use, we defined the design specifications that the material must achieve. The hoist has been designed to hold up to a maximum of 2 tons at the smallest boom length, and operate in temperatures from 4 to 41 degrees centigrade. All of the beam elements are specified to be hollow squares, and the struts on the top beam are solid rectangular pieces. The functional requirements were also defined, and it was decided that the hoist must be cheap to make and light enough to move around. To achieve this, the variables of yield strength per cost mass were maximized. The hoist has a maximum axial load of 7,159 pounds in strut A. The material should have a yield strength of 5 times the stress this load places in the strut. A safety factor of 5 has been chosen as that is the prescribed safety factor for an element in these conditions by ANSI. To derive our MPI, we first defined our free variables to be area and material. Knowing that we wanted to maximize the yield strength per cost mass of our material, we first defined yield strength to be equal to force over area. From this equation, we could say that the yield strength of our material must be greater than or equal to the force put on the beam divided by the area. To define cost per mass, we said cost per mass is equal to cost divided by mass. Knowing now that mass is equal to density times area times length, we were able to modify this equation to read cost per mass equals cost divided by density times area times length. We were then able to rearrange this equation to show that area is equal to cost divided by cost per mass times density times length. Relating these equations, we set area equal to the area equation we found from our cost per mass equation. So we can now say that yield strength must be greater than or equal to force times cost per mass times density times length, all divided by cost. To isolate for total cost, we can say that cost is greater than or equal to force times length times cost per mass times density divided by yield strength. From this equation, we can see, knowing that force and length are constants, that to minimize cost, we must either minimize cost per mass times density divided by yield strength, or maximize the ratio of yield strength divided by cost per mass times density. After obtaining 4 materials that fit our MPI, it is necessary to consider issues the user may experience in the product's life, as well as other factors that were not included in the MPI. Since one of the materials that was chosen with our MPI was cast iron, which is also the material that was chosen by the manufacturer of the product, we decided to use a decision matrix comparing the other materials to cast iron. A material with a property that was more favorable than the property of the cast iron got a score of 1. A material with a property equally favorable to that of the cast iron got a score of 0, and one with a property less favorable to the cast iron got a -1 for each subset. Looking at cross-sectional area due to yield stress, all three of the low alloy steels were favorable to the cast iron, meaning that less steel was needed. Since more metal was needed to support the load when cast iron was the material used, the part when made out of cast iron actually weighed more than it did when made of the three low alloy steels. Lighter weight allows for easier transportation as well as assembly and maintenance. The 5140 and 9255 steels, quenched at 315 degrees centigrade, had better fracture toughness than cast iron and 9255 steel quenched at 205 degrees Celsius. The cast iron had the best resistance to stress corrosion, with 5140 being susceptible and both 9255 steels being highly susceptible. Cast iron had the highest max operating temperature, followed by 9255 quenched at 315 degrees centigrade. The cast iron also had the highest minimum operating temperature at 0 degrees centigrade. The three steels all had minimum operating temperatures in the range of -18 degrees to -53 degrees centigrade. The three steels were all stiffer than the cast iron, although the cast iron is cheaper on a per mass basis. Since its yield strength is much less than the three steels, it is actually more expensive to build the part for a given load. The cheapest material was the 9255 steel quenched at 205 degrees centigrade, followed by 9255 quenched at 315 degrees centigrade, and finally the 5140 steel. Based on our analysis, cast iron, the material chosen by the manufacturer, was not the best choice for the frame of an engine hoist. Although cast iron reacts well when under stress and is very cheap, low alloy steel that was quenched in oil is able to bear the same load as cast iron with a smaller area, making it lighter weight. This makes it easier to produce and handle. It is possible that the company looked at the process and determined that along with the cast iron's corrosion resistance, maintaining cast iron is cheaper and easier than quenched and tempered alloy steel. In terms of the process used to shape the metal, the manufacturer hot rolls its cast iron. With hot rolling, the wheels are colder than the metal, so the properties, such as grain size, are not uniform throughout. This can be problematic, as certain regions may fail earlier than expected. That said, the hot rolling process is easier than quenching and tempering, and requires less time. For low alloy steel, since it is heated and quenched, it can be shaped before quenching, and the subsequent tempering reduces its inconsistencies. We decided to choose the low alloy ASI 9255 steel, quenched at 350 degrees centigrade, because it is the cheapest of the materials which ranked best in our decision matrix, has a high fracture toughness, and a very high yield strength. One downside to the 9255 steel is that it has a high susceptibility to corrosion. However, the entire structure is covered in an oil-based paint to counter this property.